Before this crossing existed, this canyon was one of the hardest barriers anywhere in the mountains. The drop is brutal, the terrain is unstable, and every meter here fights against construction.
And yet engineers found a way to stretch a bridge straight across it.
From this distance, the bridge looks impossible, almost like it was drawn into the landscape.
This is the story of how engineers built a bridge high above the clouds in one of the most unforgiving places on Earth.
Today, the crossing feels routine, but building it was anything but routine.
Every decision had to account for height, exposure, and the sheer emptiness beneath the work zone.
Before the bridge, traffic had to crawl around the mountains instead of passing over them. This crossing sits inside a rugged mountain region where geography shaped daily life for decades.
What once took hours on twisting roads could now be reduced to minutes.
That dramatic time savings is what made this project worth the risk.
But to understand how it was built, you first have to understand why this site is so extreme.
At dawn, the scale becomes clear. Cliffs, void, wind, and almost no room to work.
The engineering challenge here was never just length. It was how to build safely where the landscape gives you almost nothing.
That is the promise of this structure. One clean line across a place that used to force endless detours. For years, mountain travel here was slow, dangerous, and expensive.
Freight moved uphill, downhill, and around the canyon instead of straight across it. For nearby communities, the terrain shaped every trip, every delivery, and every emergency response.
Older crossings could serve people on foot, but they could never solve regional transport at scale.
In terrain like this, even basic logistics become labor-intensive derris. Bad weather made the old routes even more unpredictable.
One wrong move on roads like these could shut down traffic for hours.
This is why the bridge mattered. It was not a vanity project. It was a connectivity project.
The old alignment wasted time, fuel, labor, and reliability.
What looks close on a map becomes a punishing trip once elevation and terrain take over.
Even emergency access could be delayed by the geography.
Remote settlements needed faster access to markets, schools, hospitals, and regional hubs. To drivers, this route was a test of patience and concentration. Each bend added time, risk, and operating cost. So engineers stopped asking how to improve the road and started asking how to defeat the canyon itself. The canyon's depth is what made conventional bridge thinking fail almost immediately.
The first step was measuring the void with absolute precision. Wind was not a side issue here. It was a design driver. When the site is this deep and this exposed, the challenge becomes structural, logistical, and aerodynamic all at once.
Engineers compared multiple bridge types before narrowing the field. Placing major supports down in the canyon was immediately impractical because access and foundation conditions were too severe.
Building from the bottom up would have multiplied cost, time, and danger.
That meant the main structural elements had to sit where the rock was strong enough and construction access was still possible.
Then came the wind studies, because a bridge this high must be stable in changing mountain airflow.
Traffic loads were predictable. The site itself was less forgiving. Engineers modeled how the deck, pylons, and cables would move together under dynamic conditions. Once the structure was chosen, the real battle shifted from design to execution. And execution began with one essential task: understanding the mountain in exact detail. Survey teams used aerial mapping to capture geometry that would be impossible to trust by eye alone.
Every point cloud and every control point helped turn raw terrain into engineering data.
Permanent reference points gave the entire project a common geometric language.
If your survey is off by even a little at the start, the errors only get more expensive as the bridge rises.
Next came geotechnical testing to find rock capable of carrying concentrated loads. Rock cores revealed fractures, strength, and the consistency of the bedrock beneath the surface.
Those samples told engineers where they could trust the mountain and where they had to reinforce it.
Before major construction could begin, crews had to build the roads that would feed the construction itself. Even building the access routes required careful coordination because the margins were so small. Where the mountain would not yield, blasting created the platforms needed for equipment and crews.
But every new cut introduced fresh risks of loose rock and slope instability. That is why slope protection began almost as soon as excavation did. Tiny ledges became the staging ground for a structure of extraordinary scale.
In some areas, workers could only reach the work face by rope access.
By this point, the canyon was no longer just an obstacle. It had become an organized work zone.
The next mission was to lock the structure into competent rock.
Rock bolts stitched unstable layers back into the stronger mass behind them.
Shotcrete added another layer of protection against weathering and loose material.
On a bridge this tall, the foundations do not just carry weight. They resist movement, vibration, and long-term fatigue. Excavation had to continue until crews reached rock reliable enough for major structural loads. Once the excavation was ready, reinforcement turned the cavity into a structural node.
Spacing, cover, and alignment all had to match design, because corrections later would be costly.
Mass concrete pours demanded temperature control, sequencing, and uninterrupted coordination.
Proper consolidation was essential to eliminate voids and ensure full contact around embedded steel.
After placement, curing protected the concrete while it developed strength.
These hidden details would later transfer enormous forces into the substructure.
Engineers also instrumented the site so they could verify real behavior against predicted behavior. What looks like a simple platform here is actually one of the most critical components in the entire bridge. Only when people stand next to it do you understand how massive the hidden support really is.
With the foundations secured, the bridge could finally begin to rise.
Pylon construction moved upward in controlled stages, one lift at a time. Every piece had to arrive at height safely
and on schedule.
From down here, you can see the real scale of the vertical build. The tower is not just tall, it has to stay geometrically exact as it climbs.
Segment by segment, the pylon took shape above the canyon.
Weather windows controlled the pace because high winds can stop critical operations immediately. At this scale, every connection detail matters because load paths must remain exact from deck to foundation. What feels sudden in time-lapse is the result of thousands of repetitive, disciplined steps.
Inside the tower, crews built the systems that support inspection, access, and future maintenance.
Many operations happened with nothing but steel, air, and safety systems between workers and the canyon below.
Survey verification kept the tower online as it climbed higher.
Mountain weather was monitored constantly because a shift in conditions could change the work plan in minutes.
As the towers rose, symmetry became more important with every meter.
At this stage, small deviations are not small anymore. Precision now determines whether the whole system will close correctly later.
With the pylons complete, the bridge was ready for the elements that would carry the deck. The cables.
The cable system began long before installation, in manufacturing lines built around consistency and strength.
Every critical material had to prove its performance before it ever reached the site.
Individual elements were bundled into a system designed for strength, fatigue resistance, and durability.
Getting the materials to the canyon was its own logistics operation.
And now, we begin the final phase of transport.
Installation at height demanded careful rigging and disciplined sequence control.
Then came stressing, where cables were tensioned in a sequence designed to shape the bridge correctly.
This is where theory becomes physical force.
Every pull was measured, verified, and compared against the design model.
Field data fed directly back into the engineering model, so adjustments could be made immediately. Symmetry in cable installation was crucial to keep the structure stable throughout construction.
The bridge was literally shaped through controlled tension.
These cables do more than hold the deck up. They distribute load, control stiffness, and help the whole system behave as one. The deck segments were prepared off-site, where tolerances could be controlled tightly. Moving those segments into the mountains required another layer of planning. This stage was one of the most delicate in the entire build. Once a segment leaves the ground, the entire operation depends on balance, timing, and calm control.
Suspended over open space, even a small swing can create serious risk. Once the segment was seated, permanent connections began to lock it into the structure.
Segment by segment, the gap at the center became smaller.
When the last section locked into place, the canyon was finally crossed. After closure, the focus shifted from structural completion to operational readiness. Expansion joints were critical because temperature changes and movement still had to be accommodated.
Layer by layer, the deck was prepared to resist water infiltration and long-term wear.
The roadway surface transformed the bare structure into a functioning transport corridor.
Even drainage had to be engineered carefully because water is one of the quiet enemies of bridge durability.
Measured responses were compared against predicted responses to confirm safety margins.
Once the numbers aligned with the model, the bridge moved one step closer to opening.
After years of work, the crossing was finally ready to serve the region it was built for.
For the people who built it, the bridge is measured not only in meters, but in years of risk and discipline.
That patience is part of the engineering, too. Good projects respect the site instead of fighting it blindly.
This may look simple, but cable quality defines the long-term reliability of the whole bridge. At the tower and deck, each cable had to seat correctly at both ends.
With the stay system in place, the bridge finally had the skeleton needed to carry the deck.
So crews guided each piece down slowly, checking alignment constantly.
Temporary tools gave the crew the fine control needed for a clean fit.
Welding and bolt tightening completed the mechanical continuity between segments.
After each lift, engineers checked whether the real deck shape matched the predicted one. By now, months of precision had led to one last moment, the final closure. It was a technical milestone, but also a human one.
This is the moment when a project stops being two construction fronts and becomes one continuous bridge. Protective systems were added to help the bridge survive weather, moisture, and time. Utilities and lighting made the bridge safer and easier to operate day and night. Monitoring systems turned the bridge into a structure that could report on its own condition. Modern megabridges are not just built and forgotten. They are measured continuously.
Critical welds and joints were checked using methods that could detect problems without damaging the structure.
Final geometry checks confirmed that the finished bridge matched the design envelope.
Then came proof testing, where the bridge had to perform under controlled heavy loading. Opening day is the easy part to watch, but it only exists because thousands of hard decisions came before it. When you stand here now, it is hard to imagine how inaccessible this crossing once was.
The first traffic crossing marked the shift from construction achievement to daily utility. The structure that once looked fragile from a distance now performs exactly as intended.
Every vehicle crossing is proof that the design, the sequencing, and the execution all came together.
The real impact is measured in time returned to people, businesses, and public services.
What changed here was not just one road segment, but the shape of the wider network. Faster, more reliable crossings reduce cost and improve regional resilience. In emergencies, minutes matter, and infrastructure like this can change outcomes.
Projects like this can also reshape tourism by making remote landscapes more accessible.
At night, the bridge looks calm and effortless, which is exactly what good engineering often becomes.
What you are looking at is not just a bridge. It is a sequence of solved problems built into steel, concrete, and geometry.
From up here, the full achievement becomes clear. Engineers did not flatten the mountains. They learned how to pass through them.
High above the clouds, this crossing stands as proof that the hardest landscapes do not stop engineering. They define it.